4th week. So the next week will be your test 1. Okay, so it will be covered up until this chapter, all right, which is currently we are on the chapter 1 on the book. So we need to finish until the section 1.7, which is x86 addressing modes. All right. So today we're going to continue with the stack and also the flag register. And if we have time, we will finish up to the x86 addressing modes. All right. And also today, we're going to have quiz, right? So the quiz will be launched later during the class. So, of course, not all of you are here yet. So might be we will done it after we learn about the stack, right? So, do you have any questions so far? All right, so I hope all of you are quite familiar with the assembly language. So we have learned so far about the data segment, so which was recently learned. So about on how to convert that the data segment into the upper range and lower range of the data segment to the logical address and also to the physical address. Okay. Um, so we are still on the x86 microprocessor nodes. Okay. So we are now on the page 6 on the notes. If you want to refer to the notes given. Okay, so continue with the stack. So what is it a stack and why is it needed? Okay, so the stack is a section of a read or write memory. So it is from a RAM used by the CPU to store the information temporarily. Okay, so the CPU needs this storage area since there are only a limited number of registers. Okay, so because of the limited number of registers available at the CPU, so the CPU needs this storage area from the RAM. Okay, so we call that as a stack. So there must be some place for the CPU to store information safely and temporarily. Alright, so the main disadvantage of the stack is the access time. Okay, since the stack is in the RAM, okay, it takes much longer to access compared to the access time of the register. So because you need to go through the address mode, to the address bus first to take that information, all right, from the RAM, okay, to take the data from the RAM. So that's why the access time is longer rather than the register, because you see there, you already saw the architecture of the microprocessor. So the registers are within that microprocessor rather than the RAM, where the RAM needs to be accessed outside of that, right? So the stack have some All right, so for some very powerful computers, it does not have stack. Okay, it is because when it's a very powerful computer, let's say the Xeon processor, for example, so it has a large number of registers. Okay, so it can actually do much faster job without need to have accessing the stack. So but they just use the register rather than using the stack, which is available from the RAM. Okay, so all right, hold on. Okay, so how the stacks are accessed? All right, so the stack is a section of RAM, so there must be registers inside the CPU to point to it. So it must be connected to the register as you saw in the last few lectures. All right, so we have the microprocessor architecture where it has connected to the address bus, all right, and also to the other two buses, right? So the location of RAM is over here, so you need to go to the address bus and also travel to the control bus and also the data bus. Okay, so um, so the stack segment, all right. So the stack segment register, the stack pointer register is connected to the stack, all right. So these registers must be loaded before any instructions accessing the stack are used. Okay, so this stack segment and stack pointer register are located within the CPU itself, the microprocessor. So the every register inside the x86 can be stored in the stack and brought back into the CPU from the stack memory, except segment registers and SP. Okay, so SP is the stack pointer. So storing a CPU register in the stack is called a push. So what is a push? A push is storing a CPU register in the stack. Okay, so loading the contents of the stack into the CPU. So push is we store the information from the CPU to the stack, and pop, pop is the loading the contents of the stack into the CPU register. So it's called a pop. You can actually imagine that this is the microprocessor architecture, and then this is the buses connected to the memory. Okay, so this is the memory and this is the microprocessor, the CPU. This is the memory. So the stack is located inside here. And then the register, okay, so this is the register where the registers are located, okay, within the CPU. All right, so store, we push and then pop, all right, load back the content into the CPU register. So the x86 stack pointer register, so the SP points at the current memory location used as the top of the stack. As data is pushed onto the stack is decremented, okay, so it will decrement, so it will reduce one by one, okay. As the data is popped off the stack into the CPU, it is incremented, okay. Okay, so you need to remember that when the data is pushed, onto the stack, it is decremented. Okay, and then when the data is popped off, it is incremented. So increment is because it's layer, okay, so on the top, right? Decrement, it will be at the bottom, all right? So mean that the first information, okay, because the first layer, first information will be first pop off. Okay, that's why the data is pushed from the bottom. Okay, so that's why it's in terms of decrementing. Okay, it's decrement. Okay, but when for the pop off, so it's increment. Okay, increase one by one. Okay, 1, 2, 3, and so on. So when an instruction is put for a general purpose register, it must be the entire 16-bit register. Okay, so for example, we do the code of push AX. So AX is 16-bit register. Okay, so there is no instruction such as push AL or push AH, right? So it works only on the 16-bit register. Right, so that's the, so what happened if you push AL? It will be an illegal statement, right? Illegal instruction. The SP is decremented after the push is to make sure the stack is growing downward. Okay, so the stack is growing downward from the upper addresses to the lower addresses. Okay, the opposite of the instruction pointer. So to ensure that the code section and the stack section of the program never write over each other, they are located at the opposite ends of the RAM set aside for the program. Okay, after this you will see, okay, the example on how the stack is working, right? So they grow toward each other but must not meet. Okay, so of course, if it meets, the program will crash because you are already used that memory location. So you can use the same memory location that has been used by other instruction. Okay, so we look at this example. So as each push is executed, the register contents are saved on the stack and SP is decremented by 2. Okay, for example, if we have the that SP, all right, so that SP 1236 AX is 24B6 and DI, okay, is equals to 85C2 and DX. Okay, so so you have the stack pointer SP AX DI and DX. That one is the general purpose register, right? Shows the DS is the general purpose register, so you show the content of the stack as each of the following instruction is executed. Okay, first we want to push AX, then push DI, and also push DX. Okay, so we start with the SP. So start with the address of 1236 for example, right? So start with the address of 1236. So SS 1236. So it starts there, and then we need to push AX. Okay. So we push AX. So now the SP, the stack pointer, will become to 1234 because we only include, okay, at each location only 4 bit of information. All right. So that 4 bit and then another 4 bit to the upper of the stack. Okay. For example, you have AX24B6 Okay, so first you put at the SS 1235, okay, 1235 S, okay, 24, and then you put B6 on top of that. Okay, once you finish that, okay, at 1, 2, 3, 4, and then it will be continue with push DI. So what's the information of DI? So you will have 85 C2. So you put 85 and C2, and then now the stack pointer becomes 1232. All right. Then after that, again you push the DX. Okay, DX we have 5F93. So it start again the 5F93. Okay. So as you can see that it is actually from the most significant bit, the higher bit to the lower bit. Okay. So you can see that it is actually in the decremental. Okay, because if you see that inversely, it's actually from the bottom. Okay, so but it is stackable. So because you want to see the stack, so it is stackable like that, stack, stack, and stack. So actually we consider this, right? So if you see that in the, if you see that this one in the reverse direction, okay, you reverse that. So you see that this is actually the bottom part, all right? Because 1230, and then this is 1236. So this is what is called as decrement, all right? Decremented by 2. So it decrement, keep decrementing. 1236 to 1234 to 1232 and 1230. All right? But the information is stackable, all right? So that's why you put the higher bit first rather than the lower bit. Okay, so you put the higher bit. Okay. For example here, 24B6. Okay, 24B6 and 85 C2, 5F and C3. 5F and 93. All right. Okay, since okay, because we are saving the content of 16-bit register, because we have an 8-bit and also another 8-bit, so we have a lower one and upper one. So the lower 8-bit and the upper 8-bit, so we need to stack it for every 8 and 8. All right. So meaning that for every byte, so 1 byte is equals to 4 bit. Okay, SP, the stack pointer is decremented once. Okay, so okay, this is just repeating what I have explained to you. Okay, so first we have AX24 H content of AH, right? Because for AX we have AH and AL, all right? Saved into the memory with the address of 1235, and then AL stored in the location of 1234. Okay. Right. So in the lower byte is always stored in the memory location with the lower address. Okay. Now we look into the pop, right? So for the pop, it will be reversed from the lower bit, okay, from the lower bit to the higher bit. Okay, so let's see here. So assuming that the stack shown below and SP stack pointer equals to 18FA shows the contents of the stack and registers as each of the following instructions is executed. So we already have information there. So we want to pop, let's say you want to pop CX, right? So we want to put the information into the CX. So we pop and CX. So this information will be released, okay, to the CX. So as you remember that, so this will be 23 will be on the lower 4 bit, lower 8 bit, and then this will be on the on the upper 8 bit. So CX will be 1423, okay, as given here. All right, and SP, okay, so the stack pointer, okay, starting from here, the stack pointer is SP18FA now becomes SP18FC. Okay, it increments by twice. Okay, so it increase. And also similarly, if we do pop DX and pop BX, of course it will increment to, right, increment 2 and also increment 2. Okay, so from A to C, C to E, and E to 1900. All right, so we have, let's say over here we have the next DX will be 2C 6B, and pop BX, so BX will be F691. All right, so of course the SP will accordingly increase. Okay, so as you can see here. All right. Okay, if the data, all right, or the data actually remains in the memory, it is not accessible, okay, since the stack pointer is beyond that point. All right, if the stack pointer beyond that point, then the data that is located, okay, located beyond than that is not accessible. Okay. Okay, the exact physical location of the stack depends on the value of the stack segment registered and the stack pointer. Okay, for example, to compute the physical addresses for the stack, shift left stack segment and then add offset stack pointer, the stack pointer register. Okay, for example, we have SS. Okay, the stack segment equals to 3500, and the SP is FFFE. Okay, and then we need to calculate what is the physical address of the stack. Okay, so you still remember? So what we have learned last week? So we have, okay, so SS will be the lower, okay, so the lower segment, okay, and we add that, okay, with the upper segment. So we have the physical address 3500, and we add 0, right? So we add 0 and add with FFFE. Okay, so you got the answer of 44FFE. Okay, calculate the lower range. So the lower range will be 35000. Okay, so the upper range will be 44FFF. Right? Because you add 000, and then for the upper range, you add with FFFF. Okay? And then the logical address, so it will be 3500 double dot FFFE. Okay, so that's the stack's logical address. Okay, so can a single physical address belong to many different logical addresses? Okay, let's see. We observe the physical value of 15020. So many possible logical addresses represent this single physical address. Okay. So you can see that. So it is possible actually. All right, it is possible. So we see that we have the physical address of that. Okay. We have 15020 and also the logical address 1000 at 5020. Okay, so it can be that, okay, because the logical address is actually you add, okay, so 10,000, right? You have 100, so you add one more zero, so it will be 10,000 plus 5020. Of course, it will become the physical address 15020. And then if you have the logical address of 1500, so you add another zero and you add with 0020. So at the back also you have similar physical address. So it can be in many arrangement, right? It can be in many arrangement because the logical address, the maximum possible address is at the back is FFFF. As long as that does not violate that, so you can have multiple logical address for one physical address. Okay. Okay, so this is an illustration of the dynamic behavior of the segment and offset concept in the ET80 CPU. Okay, when adding the offset to the shifted segment register results in address beyond the maximum allowed range. So if it is beyond FFFFF, okay, when you offset, also we got FFFFF, right? So wrap around will occur. Okay, for example, what is the range of physical addresses if CS, okay, equals to FF59? Okay, so the lower range, okay, so the lower range, so we add 0 at the back. Okay, the lower range is FF590. Okay, and then how about if we add FFF, so which is the upper range, right? So because we want to know what is the upper range of that, so it will wrap around. Okay, for example, so we add FF590 plus FFF. Okay, you look at the back here. So if we have FF590 add with FFFF, so what will you obtain? So you will obtain F, and then so F added with 9. Okay, so how many? So because F is already 15, okay, 15 add with 9, how many? All right,
54
so it will become
minus 16.
yes. Okay, so how about you get this as 8? All right, so
24
over here,
minus 16.
okay, so because F is the maximum, all right, so you will add that, okay, with 9, it will become 8 here, and then this will become, okay, this will become 5, and then this will be ignored, okay, because it's already exceed that. Okay, all right, so because it exceeds that, so we take just F over here. All right, okay, so that's it is actually okay, you see that, so initially we have FF590, okay, and the range goes to FFFF and it wraps around. Okay, because first, all right, first we need to add all of that. Okay, for example, we add FF 590. So this one become F. So when you add again F with 9, so what will the value? So it will become how many? What's the number?
8.
So F in hex. So maximum will be F. Okay, from 0 to 9. Okay, and then A, B, C, D, E, F. All right. And then what's the value of that? So how do you perform the addition of this? You need to go back to the, if you see the addition of that, on the section okay, on the chapter 0, right? On the chapter 0. So F is 15, all right? So we consider F is 15 and we add with 9, so it will become 14. All right, so you write 4. And then you need to add 1 to here. All right, so 15 plus 6, so it will become 21. All right. So when it becomes 21, hold on. All right. For the first one, okay, it's okay. F. So 9, F 15 plus 9, it will become 14. All right. 14. 14 is E, right?
E.
E. Okay. So it will be E. Okay. And then you will add 1 to that because you have the additional of from what is left from the 9 plus F. Okay, so over here, so let's say F is 15, so 15 plus 9, it will be equals to 24. All right, so what you need to put here is the one that 24 minus 16. So what do you get? You get 8, right? So that's what you need to put. Okay, so that's correct. So F 8. Okay, so 1 will be carried there. Okay, so that's how to do that. Okay, so F add with 5, so it will be 20. All right, 21. Right, 21 minus 16. So you obtain 5. Okay, you add 1 more here. So of course it will be F8 5, and then you add 1 here. So F plus F. So 15 and 15. Okay, 15 plus 15 plus 1. So 31. All right, 31 minus 16. So it will be 15, right? So 15 is F. Okay, so you got F and you add 1. over here. All right. So it will be, right, so the last one, it will be 0 because, okay, so you have a f, so if f you add with 1, all right, so you have 16, right? 16 minus 16 will be 0. Okay, you got that? Is it?
Doctor,
Yes.
shouldn't there be a 1 carried over to the next one after 16?
Okay, because you need to carry over, because this number, okay, let's say first one, 0 add with f, right? So you have 15. Okay, 15 is okay because it's not yet exceeded 16. Okay, you need to remember that for the hex number, you have maximum of 16 bit. Whenever you don't exceed 16, you don't need to carry over 1 to the next one. But if it exceeds 16 bit, all right, let's say the number is 17 and so on, so you need to put carry 1 on the next number. Okay, so for example here, okay, 0 and f, f is, so the value is 15, right? So we just put f because 15 is not exceeded 16 yet, so it's okay, so we don't put 1. But when 9 plus f, so f if we consider as 15, right? Because the number from 0 until f, so f is 15. So 15 plus 9 is 24. So 24 exceeded 16 bit, so we need to minus 16. Because when you minus 16, we will carry over 1 over the next addition, alright? So the next digit of that. Okay, so 24 minus 16, so you get 8. Okay, so you get 8, so you put 8 there and then you add 1 over there. So when you add 1, so this one you just add 1 more. So f plus 6, so meaning that 15 plus 5 plus 1, so 21. So 21 minus 16, you get 5. So you put 5 because it is exceeded 16, right? So you put another 1. Okay, so you add and until the last one, so you get 0. Okay, so that's why you obtain the answer as a 0F58F. You got it? Are you okay? Or you still need more explanation?
I think okay, Doctor.
Okay. All right, so you look there, as you can see that, okay, so we have actually is a little bit, what we call that, right, the range, okay, the range will be wrapped around, all right, meaning that actually this value should be on the top, right? If you look back, if you have, let's say if you use the lower number, for example, let's say if I use 0, 1, 0, 2, for example. Okay, what is the my number? So the lower range will be 0, 1, 0, 2, 0, right? So that's the lower range. So what is my upper range? So I add with FF, FF. So my upper range will be F, F plus 2, so it will be 17. 17, so you have 1 and you add 1. So you have 16, 0, and you add 1, alright? And then F12, so F17, so it will become 1 and 1. Okay, it will be this number, alright? So the range will be from 0, okay, from 0, 1, 0, 20 till 110 1F. Okay, you see that? So this is a bigger number, right? So it has no issue. So what is wrap around? So wrap around, the number that you add here is become smaller than your lower range. Alright, this is actually your lower range because you add with 00, so you obtain this. So it wraps around, it goes back to the lower number. So this is actually your range. Okay, compared to the range that you should have, okay, from, let's say from here to there. Okay, but it is from here to the lower number. Okay, so that is what we call that as wrap around. Okay, in calculating the physical address, it is possible that two segments can overlap. Okay, so let's say we have on your left, so we have the non-overlapping segments, for example. So we have CS2500, so it starts from the lower range of 25000 to when you add with FFF, so you have 34 FFF, okay? And then you have DS, the data segment, and then stat segment. Okay, so that is not overlap, right? So because it is at different, it is at different location of the memory, but you can have the overlapping segment as well. So what happened is there is an overlapping segment. So you can see that. Okay, so here it will be up to, so here it is not overlap, right? Here is, there is no overlap, okay? Here is also no overlap, but here it is overlap. Here it is overlap. So you see the maximum range of DS 4050, it is this one, 54504FF, okay? But when the lower range of SS 500, which is lower than this, so it will be overlap. Okay, so that is the overlapping segment. Okay, so that's an example of the overlapping segment. Okay, so as I mentioned to you during the start of the class, we're gonna have a quiz. Alright, so this is actually related to the assembly language quiz, which is part of your career marks. Okay, so I'm going to share you the link, alright, the link on the WhatsApp. You can join the session. By the way, you have any questions so far? Okay, you can join that. Right, I have shared you the link. Okay, so you can see the quiz now. All right, I already seen Nurin. Okay, Alif, Lavina. Okay, you can see your results. Let me share you. You can discuss. There's no problem to discuss for the quiz if you want. So the quiz is actually for you to get a better understanding. So I expect that I hope all of you understand what we have learned so far. You can try multiple times. So Natasha, you need to try again. So you got wrong. Ishira also got wrong answer. You need to try again.
How many attempted?
You can do as many attempts as possible. So I'm giving you the time, right? I'm giving you the time until 4:30 to finish 5 questions.
Thank you, Dr.
Okay. Okay, Liu Ziyu, you got it correct. Okay, congratulations. For the first question, okay, Nick also got it correct. Okay, Alif got it correct as well.
Oh, doktor tulis jawapan je
Ya, tu jawapan je.
Oh, patut yang salah.
Doktor, saya pun salah tadi.
Okay, never
Sama,
mind.
doktor.
Boleh
Kira
try
sekali
lagi.
je letak.
Apa dia?
Saya letak jalan kira. Answer satu tu sama.
Just letak. Just put the answer, okay?
Answer.
The answer. Right now, only 1, 2, 3, 4. So most of you only get only one correct. Nobody has yet got two correct answers. Allah.
Anak ke?
Okay, so I found that. So, okay, some of you, okay, Haziq already got 3 of the answers correct. Okay, and then some other of you also got, okay, Izzuddin got 3 correct. Okay, so I think I don't have time to finish the other 2 section on the registers and also the x86 addressing mode. So you just continue with the quiz. So just do it. All right, so I will stop the session soon. Okay, so if you have any question, just let me know.
So to try again, rejoin this quiz.
Apa dia?
Kalau nak cuba quiz ni lagi sekali, rejoin.
Dia tak boleh multiple times ke? Dia tak boleh.
Tak, once I'm done doing the quiz, it says I have to wait for next activity.
Oh, okay.
So do I
Ah,
attempt another?
buat balik lah, buat attempt, a new attempt.
Okay.
Okay, so I will stop the Google Meet session. Alright, so to answer that, I think since many of you are still not, most of you are on the question number 2. Right? So you can, I think I will give you until 5 to finish that. Okay, so I'll start the Google Meet session. If you have any question, you can ask me on the WhatsApp. Okay. Okay, last before not least, let's take picture. Okay, for today's attendance. So please turn on camera for all of you. So don't worry, you have until 5 to finish that quiz. Okay, come on everyone. Okay, I'm gonna count from 10, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Cheers. Okay, one more shot. Oh, someone is also inside the car as well. All right. Don't drive and do your quiz. All right. Please stop. Okay. Don't drive and do your quiz. It's dangerous. You still have time until 5 to finish your quiz. All right. Okay. So I see you again on Thursday. All right. So all the best with your quiz. So let me know on the WhatsApp if you have any concern about that. Okay, so bye-bye. Okay, Assalamualaikum.
Thank you, Doctor.
Thank you, Doctor.
You're welcome.
Thank you, Doctor.
Thank you, Doktor.